All right, I want to do a video on using an oscilloscope as a spectrum analyzer. So let's start out using a real spectrum analyzer first and get used to the things that we want to show on the oscilloscope on the spectrum analyzer first, so you know what they're supposed to look like, okay? And so I have a square wave. I have a 100 kilohertz square wave coming into the function generator, and I'm sweeping from 50 kilohertz to 575 kilohertz so I can see the first three harmonics of the square wave. And you can see that we have these broad peaks. Well, that has to do with the bandpass filter of the oscilloscope. The smaller the bandpass filter, the more resolution you see. We kind of get some hints here that there might be something between these peaks and stuff, but our band pass is causing us lower resolution, okay? So right now we have a resolution bandwidth of 10 kilohertz, okay? And so I'm going to change the resolution bandwidth, and I've just changed it to 3 kilohertz. And you can see now we're seeing these narrow spikes. There's still some width of the bandpass filter, so that's what we're seeing here. And I can go narrower, and we can see that there are some things here. Let me pull up the amplitudes, we can see everything here. So you can see that's sort of what's going on here. We have these large peaks, and then we have these little peaks in between. So this is the fundamental, the second harmonic, third harmonic, fourth harmonic, and fifth harmonic. So the odd harmonics are higher, and the even harmonics are lower. So here we are using a spectrum analyzer in the way that you would use it. I can even make the resolution bandwidth smaller. It takes a long time to sweep it. Now we have a 300 hertz resolution bandwidth. So we can see even finer details. So you can see that on a regular spectrum analyzer, you need to take care of what bandpass filter you use. If you go too big, you can't see anything at all. That was 30 kilohertz. Here's 10 kilohertz, 3 kilohertz, and 1 kilohertz. So resolution bandwidth. Okay, so now let's see if we can't see this picture on an oscilloscope. All right. I'm on the right-hand side of the camera today, so that's kind of a little bit odd for me, but that way I can reach in this way and not get in the way of the camera. Okay, so this is what we're seeing coming into the oscilloscope. So down here, I'm coming in with a 50 ohm, what do you call them, 50 ohm load, a 50 ohm termination, that's it, 50 ohm termination coming in oscilloscope. So we need to set up the oscilloscope for that. I'm not using a scope probe, I'm using direct input. So I'm going to have to come here, and where the probe says times 10, I need to say it's times 1. So we don't get that math in the way. Okay, so here's our signal coming in, and we're at 100 millivolts division, so it's plus or minus 100 millivolts, and it's 100 kilohertz, right? Okay, so how do we see spectrum on a oscilloscope? Well, you can't, unless you have a digital oscilloscope and you have one that has a mathematical function in it called an FFT. Okay, an FFT is called a fast Fourier transform, right? So even most low-end scopes these days have an FFT in them. This is only about a $360 oscilloscope, something like that. And it does have an FFT, so let's go ahead and see if we can use it. So the way that you do it in a Rigel is that, let's see here, I'm zoomed in a bit too far up here. So there's a math function, so I'm going to hit the math button here, all right? And over here it says operator, and I click on operator, and there's a bunch of things I can do: a plus b, a minus b, a times b, a divided by b, and then the next one is FFT. That's the one I want, FFT. And then you need to say operation on. Okay, so that turns the operation on. So now down here we have an FFT. All right, so let's go back over here. Okay, now I hope this shows up on camera, because Rigel uses a purple trace down here, and I don't really like it. Anyway, let's see here. Okay, so first of all, it doesn't look anything like the spectrum analyzer showed. All right. So how do you get it to display what the spectrum analyzer was displaying? Well, it's actually very, very complicated. So the first thing you can do is you can change the horizontal sweep. And if you change the horizontal sweep, this thing here will change. And it is very, very small, but it's starting to look like a peak and then a tiny little peak in the middle. Hope that shows up on camera. So we need to make that bigger. All right, so how do we make that bigger? So we can, in the FFT operations, we can set the center and the divisions and the offset, and then just a down arrow, you can get to more stuff. So here's more stuff, all right? And here up at the top is a scale, and I can make it bigger, but then it whoop, fell off the bottom. So it's a really lousy way of doing things in here, but let me set it to 20 dB. So it's also in funny units. It's in dB volts, which isn't great either. So we can go back. We can say, okay, we want to have an offset, and that offset is basically like this button here on the vertical. You can set the vertical position. Well, this sets the vertical position, but they call it something else. They call it offset. So we can move it. And if you look over here, there's a little thing. So I'm going to move it all the way to the top, just so we can see a nice big picture. Okay, so I'm up at the top here now. All right, so now we have a better looking picture. Now if I go back to this division thing, I can make it even bigger. So let's do 10. 10 looks good. Let's stay with 10. We'll go back to our, we'll go back to our offset, and we can move it up so we can see things. Okay, there we go. Now we're starting to see something. All right. So it's in the middle, which is really silly. A spectrum analyzer, be nice if it was over there. I mean, you're wasting all of this room over there, but you can do that. You can say center. You can take your center button, okay, and you can move it. So that's now your horizontal position. So you can move the whole thing over, and you can set that center up anywhere you want it to be, okay? So let's set it up to be 300 kilohertz. So 300 kilohertz would be the third harmonic. Fundamental, second, third, fourth, fifth, right? So there we go. Now we're getting there. Now we're getting there. Now we want to zoom in even farther this way, span. So we can go to what do they call it here? Hertz per division? These things just labeled all wrong as far as I can tell. Oops, I went way, way, way too far. Okay, let me go back out. Oh, what? It's got kind of touch. Yeah, there we go. Now we're starting to look like that picture we had on the spectrum analyzer. Okay, we have peak, peak, peak. Okay, now we're looking good. Then you're going to say, well, that looks terrible. What's all that noise and what's all the, why aren't these nice shapes? Now remember on the spectrum analyzer we played with resolution bandwidth. Well, we need to play with something different over here. It's not resolution bandwidth, it's something different. And to get there, we're going to window down again. And that was a Freudian slip. So we're going to look at the window function. Okay, so what is a window? Okay, so we have window, and it says rectangle. You go, oh great, oh we're looking at a rectangular window, and maybe I can set that to a square. No. That is not what it means. A window function is a mathematical function, and it is set to rectangle right now, but that's just a mathematical function as well. If I hit the button that says rectangle, and I click it once, it goes to Blackman. And look at the picture. The picture is now starting to look more like a spectrum analyzer. That's Blackman. Underneath that is Hanning. Hanning looks like a spectrum analyzer. Hamming. So there's Hanning and Hamming to be very, very confusing. H-A-N-N-I-N-G and H-A-M-M-I-N-G. And then there's Flattop. Flattop doesn't look very nice again. And there's triangle. So why all this stuff? And why do they start with rectangle when Blackman seems to be much nicer? Oops, I just hit the wrong button. Math. Okay, so I'm going to hit the math button, come back to here. Okay, there we go. So we're going to go here to window again. And let's set it to Blackman. And Blackman looks very, very nice. And so I would say that everything is looking pretty good now. We're getting a nice display. I can hit this horizontal. I got to show you something here that's kind of, it's very, very non-intuitive. But if I click the horizontal switch, you can see the picture changes. And I can see more harmonics and I can see less harmonics. I can go back to that picture we had. So what's going on there? How come it acts so bizarrely? Again, it has to do with mathematics. It has to do with how many data points we've captured and the mathematical function to get to this fast Fourier transform. And it is actually very, very complicated. And you kind of have to have a math degree to know how this thing works. So I wrestled a lot with this video, like how much detail do I go into? How do I bring across these ideas easily? My channel is all about trying to get very, very complicated ideas across in a very, very simple manner. And unfortunately, there really isn't a good one for this. So the best thing I can tell you is learn all of these horizontal and vertical things because they're very non-intuitive. So play with the horizontal position, which they call offset. Okay, change the horizontal position, which they call centering, and then play with the scaling, which they call scaling here, and then get a good-looking picture, and then just push this button, this window button. Just push it, and just look at the different ones and see which ones you like. So for particular applications, some buttons are better than others. Some of them are more frequency accurate, some of them are more bandwidth accurate, some of them are more amplitude accurate, and it all has to do with mathematics. And again, it's very, very complicated, but I bet 99% of people who have Rigol oscilloscopes have never pushed that button. It's hard enough getting the FFT to work correctly, but if you ever do, you're probably going to be really, really disappointed in saying, well, that doesn't look like a spectrum. That's not the spectrum I'm used to. Push the button and get something that looks a little bit nicer. So I like this Blackman. So the oscilloscope has some functions built into it, like it has rectangle and Hamming, but there's more than that. They just aren't in this instrument. There are more mathematical functions, but Rigol just implemented these. So I think I want to stop here and let's see. I'll show you one more thing before we stop with the oscilloscope picture, and that is that you can use cursors, okay? So you can go to cursors, you can turn them on, we can turn them on to manual, we can do horizontal ones, and notice that we're doing cursors up on this picture, and we want to do cursors down on this picture, so I think I need to hit the math button, and cursor, my cursor is not, say, how do I get down to the math? I'm going to do math. Okay, now I'm going to do cursor on manual. Nope. Oh, I'm sorry. I remember now. See, it's really, really complicated. You have to do source, okay? So it's set to source 1. We want to click it and go down to source math. So we click on source math. Now our cursors are operating on that bottom window. Yeah, could it be any more complicated to use? But get a spectrum analyzer. Sometimes you really have to use this though, especially if you in operating in the DC to 20 kilohertz range. You're really better off using the FFT because the regular spectrum analyzers stop at 10 kilohertz. They just won't operate below that. So at really low frequencies, you really kind of need to use one of these. You can buy low frequency spectrum analyzers. They're quite rare, so it's not likely you will ever own one of those. All right, so once we get into our cursor, now we can move the little lines back and forth, and we can set, you know, what this frequency is, and you can go to vertical, and you can set what amplitude that peak is, or another peak. And you can use cursors to measure things off of here. Now, they're going to be in funny units. They're going to be in dB volts. So there's a logarithm in there, and it's a factor of 20 in there. So if you really wanted to make measurements, you have to do that math to get back to some other thing, or dBm or something else. You'd have to do mathematics to get back and forth. I haven't figured out a way to actually get this thing to read out in dBm or even dB power yet. It's always dB volts. Anyway. Maybe somebody else knows, but I don't know how to do it yet. But I think a lot of times when you're using spectrum analysis, you just want the picture. You just want a picture and to see what's going on. Do I have a harmonic? Do I not have a harmonic? So this is what a square wave looks like. This is what a sine wave looks like. We get just the fundamental, and the other harmonics are suppressed. This is a square wave. We get all the odd harmonics. This is a triangle wave. We also get the odd harmonics, but they're at a different fall-off rate. So if we go out here and we look, let's go out one more here. If we look at how fast they roll off, these harmonics are rolling off. We go to a square wave, they roll off slower, and we go to a triangle wave, they roll off faster. So that's all theory. You can look into that, but you know, it is acting like a spectrum analyzer, and it is doing its thing. It's just rather complicated to look at. So yeah, so let's look a little bit on window functions. All right, I'm not going to spend a lot of time on this. I just want to point you to the right resource. So one of the really best resources I found online was Wikipedia. If you do a search on window function, window function on Wikipedia, you'll get this nice write-up on mathematical window functions. So it starts out here in signal processing and statistics. A window function, also known as apodization function or tapering function, is a mathematical function. Okay, so certain fields of science will use the term window, and certain fields of science will use apodization. Like, you know, I was in optics, and we would apodize things. So it is a mathematical function. So if you think of a bell-shaped curve, that is a window function. A bell-shaped curve is a window function. All right. So so they talk about a little bit about usages, okay? And then the very, very next page, they talk about, just a little bit here, they talk about applications. And they say that it's used in spectral analysis, modification, and resynthesis, okay? And so spectral analysis is like the #1 use of window functions. And so, yeah, just something you need to know if you're ever going to use a spectrum analyzer that's based off of an FFT. And let's see here. It talks about all the mathematics, noise bandwidth, and symmetry, and stuff. But what I really wanted to point out here, well, like I said, I pointed you to this document, and so, you know, go read this document if you're really interested. It's really well done. So here's a list of window functions. Okay, so what is a rectangular window? A rectangular window says with n number of samples, treat all samples equally. Just sum them up. This is like an average, right? Also called a boxcar averaging, right? You may have heard that term, boxcar averaging, which is just whatever's in the box, add it in, and that's all there is to it. And if you do a Fourier transform of this box, you'll end up with that, which looks a lot like that first picture I showed you on the FFT. You had these big skirts, you had this big roll off over here, and that's why, because it defaults to rectangular windowing. Okay, so this boxcar averaging. All right, there's another one called triangular windowing. Now the Rigel did not have this one built in, and you would get something like that. Here's Parson windowing. That wasn't in the Rigel. Oh, here's a Welsh window. So you can see that certain shapes will look strange in the frequency domain. So this is in the sample domain. This is the frequency domain. Okay, let's keep going. Cosine sums. So because FFTs are all based off of sines and cosines and stuff, there's windows that are related to sines and cosines. And so here's a Hahn window. This is a pretty famous one. And a derivative of the Hahn window is the Hamming window. Okay, so here's the Hamming window. Now the Hamming window basically looks like a bell-shaped curve, right? And so it's going to give you a very narrow peak. So having this big wide peak, this one narrows it down. So you have this really narrow peak. You have a little bit of ringing right at the end of it, but it narrows it so you can get better frequency response. Let's see here. Nuttall. Here's Blackman Nuttall. So I think the Blackman function is a series of them: Blackman Nuttall and Blackman Harris. The Blackman Nuttall has a nice narrow pass in everything, and then everything else is equal amplitude out of the passband. This one has some ringing out of the passband. Okay, so there are different types of even Blackman functions. Flattop function. The Flattop function should look familiar if you have ever looked at the Tiny SA. The Tiny SA has filtering built in a DSP, and it ends up having filter characteristics that to me look like flat top windowing. The flat sides are flat in these things, and there's ringing outside the band, and that's one of the issues with the Tiny SA. It doesn't have a Gaussian filter. It kind of has one of these filters. Here is the official Gaussian window. So this is the Gaussian window, otherwise known as the bell-shaped curve. So yeah, there's that one. Let's see here, generalized normalization window. Like I said, window functions are many. Kaiser windows. Anyway, let's see if there was any other ones here. Oh yeah, see, there's tons of them. Exponentials, bezels. I've used a lot of bezel functions in my day. And then if you look at a comparison of all of these filters, so here's rectangular, Hamming, Tukey, Blackman, and Flattop. So they all have different frequency responses. So why do you need to use them in an FFT? It's the basics is that if you do an FFT, you want an infinite number of data points. And you don't. You have a finite set of data points. And because you have a finite set of data points, you will introduce errors. And you need to approximate what happens outside of your data set. And you do that with these functions. So you can imagine it's some type of averaging. So if you have data that's kind of going down, you want your averaging filter to also go down. You don't want it to just go down and then stay flat. You want it to continue. So these normalization functions, these window functions, allow you to use a limited number of data in an application where you need an infinite number of data. Okay, so anyway, yeah, read up on window functions. Go take your Rigel or your Siglent or O1 or whatever and push the button. It's got a window function button. Push the button.